Hello everyone, this is Mohsen Saraj from Ozen Engineering. I'm a senior application engineer for Ansys Safety. In this video, I want to talk about how to model open channel flow in Ansys Fluent by volume of fluid method. Hello everyone, this is part 3 of the series of the blogs for open channel flow modeling in Ansys Fluent using volume of fluid method. In this part, I want to show you how to model the open channel flow, that when we have the flow in circular channels, and this is a kind of application for underground tunnels. These tunnels can be used for the water systems, okay, and the difference between pipe flow and this open channel circular flow is that in pipe flow we don't have free surface. This is one very important things here, but in open channel flow we have a free surface. Another things is that the flow speed up in pipe flow by pressure, but here in tunnels and in this open channel circular channels, we have the flow usually speeding up by gravity. And this is another things is that usually the velocity profile is maximum at the center of the pipe flow, but in open channel flow in circular channel, no, it's usually a little below the free surface of the water here, that we may expect to see the maximum velocity there. So let's see what we can do here. This is the model I created. I have as you can see, I have two channels, circular channels joining together here to the main tunnel, and you can see that the radius for each of this branch, it is 200 millimeter. They are joining to the main tube, which is the which has the radius of 400 millimeter, and this tube is about 6 meter long. If we check the inlets, as you see that here outlets at the end of the larger tube and walls, so it is like it could be underground tunnels that we can have. So and here also I define it as a wall. So here these are the boundary conditions that we use it in Ansys Fluent. I can transfer that to Fluent watertight model to Ansys Fluent meshing. I will do this, and I will show you what we have in Ansys Fluent. Let's get there. Okay, I meshed it, the model. These are circular tubes, and this is the larger tube. Sometimes we call it shaft, the larger tunnel. I meshed it, and you see that the two inlets and one outlets that we have. General, as you see that for the general, be sure that you activated the gravity in negative, here for this example, in negative y direction, and we will run the transient simulation. For setting up volume of fluid method, I choose volume of fluid method, activated the open channel flow, and also have the implicit body force on. These are two minimum phases for the phases, I use air for primary phase because we have much lower density for air, and uh, secondary phases we use water for that. And we can you know that we can define the materials here. For the new material, I can use the Fluent database that we have for the fluid. Water is almost at the end. This is water liquid. I can also assign or change these uh, properties for specifically for the density. Okay, if I copy that, I already done that. The water liquid added to the list for the materials. We have to also say this for to Ansys Fluent about the interaction between the phases. I consider constant surface tension that it is 0.072 Newton per meter, and also the model for the surface tension, it is just continue. So the volume of fluid method now is set it up. By default, we have for the turbulence modeling, we have k omega SST. I just keep it as is. And material, let's check boundary conditions for the inlet. Okay, again, pressure inlet here that we have. Okay, I just keep it as is. I activated open channel option here. Again, here I have to say this to the program, to the solver, that where is the free surface, what is the water level here at the inlet, what is the velocity, and what is the bottom level of the channel. So these are the 0 and the minus 0.02. It is according to the system dimension, to the dimensions for the geometry that we have. In your problem, it could be different. This is for the inlet. Okay, same for the other inlets. For the outlet, I use pressure outlet. Okay, just keep it as is. For the momentum part, for multi-phase, again I activated open channel. I have to say this to the solver, that where is the free level at the outlet and where is the bottom. And you can see that the bottom of the larger tube, okay, is lower than the bottom at the inlet. So we don't have open boundary condition here. This is the main difference between the previous cases in part 2 and part 1, that we have a trapezoidal open channel, and we're using this volume of fluid method there, but and the top faces on those on these parts, the cases that we use, they did these open face, these top faces were open to the air. But here we have everywhere the wall at the the walls all around the water and air for the smaller branches, tubes, and the main tube here. Let's see what else we have. Methods, again same. Be careful that here I use simple to see that what's going on between pressure and velocity. Presto, be careful that this is the scheme that we use for pressure discretization, and second order we use for the discretization of the momentum, turbulence, or other parameters here. I keep the controls as is, so same level of the normalized residuals here. Report definition, again, if you wanna see that what you can have. Okay, you can define different things in at a specific surface, at the whole domain or part of the domain, as a volume report or other things that we have. I already defined at the outlet for the velocity. This is area weighted average. It is one of the surface report that I can have at the outlet for the velocity magnitude, and also for the velocity at the whole domain. Uh, Other things is that I already defined a region. I call it region initial, similar to the previous cases in part 1 and part 2. And these dimensions, again, according to the uh, to the geometry that I already built in. I use this for patching. I initialize it, the model. You could go to initialize from a specific part like an inlet or outlet. Okay, I usually go with the inlet in these cases. As you can see that here I have 0 for volume of fluid for the secondary phase for water. It means that when I initialize this system, this case, everywhere is air. Okay, but I want to start with some water inside these tubes. So this is what I do, that I use patching. This is patching. Okay, that I go for phase water for volume of fraction of 1, that indicates that we have water, and assign it to the region. So if I already done this, I patch it. Okay, if I click patch it, I already patched this there. So it means that now by this patching I have water inside the domain before starting the simulation at the some level, and this is the level that I have the free surface defined before, or already defined at the inlets and the outlet. And then running the calculation, I just keep same time steps for the for the 5 millisecond time steps, and it defined to the how many uh, time steps you want, and start running. Before starting running, uh, I already defined some contours, and based on these contours I defined the animations. Okay, I use these contours here, okay, to define the animations. And then after finishing the solution, I can come here and check the animations here. Let's start the solution. Okay, the solution is done, and I started post-processing. Look at some of the contours that I use it. It is only for the larger tube, that you see that where we can see here exactly where is the water level, and it is wavy. Okay, for the free surface over the for the water over free surface, you can see that when the velocity merging getting into the main tube, okay, the velocity increasing, but at here it is no, the velocity is about 1, and as you see that here it is like a almost dead zone, very small amount that we can have. Okay, and it is wavy free surface based on the waves that travels there, and also affected the branches, the flow into the branches. And for the volume of fluid, okay, this is what we can see, that where is the water into the branches and into the main tube. uh, besides that, we can define new, uh, for example, for the pressure, new contours to see that what is the level of the, and what is the distribution of the pressure. Again, you see that maximum here at the bottom, which is in line with the hydrostatic pressure that we can have, and this is like a almost zero, which is like a air pressure. So somehow we can see that where we have water, when we have air into the domain. On top of that, we can have turbulence. Okay, that if we check the free surface as well. Okay, and this is for to see that what's going on inside. This is for energy, turbulence energy for intensity. You can see that, okay, that here, okay, I can see more intensification into the water, into the turbulence of the water, because of the interaction of the incoming streams from these two branches, and also at the outlet that it is because of the outgoing flow that we can have. So different parameters like velocity, the way that the flow streams interact together, and pressure, turbulence, or whatever, I can find it here. uh, I can define vectors. I already defined that for the magnitudes of the vector, from inlet toward outlet. Okay, that I have it here, that you can see that, for example. Okay, uh, as you see that we have a higher value for the velocity when the flow from the branches getting into the to getting in touch together. Okay, that you can see that, okay, higher velocity for the flow, and here you can see it with this arrow keys. Okay, that at the free surface, first of all, you can see that the wavy and disturbances of the of the flow that propagated over the free surface, that it is scaled by the velocity magnitudes. And here a kind of uh, more uniform free surface. Okay, after the flow is developing along the main tube, and again the flow disturbed at the outlet. uh, we can have these vectors only in terms of the z velocity. Okay, z is what is the velocity in line with the main tube, main tunnel. Okay, let's see that. As you can see that, okay, again you see that the flow is coming back, so it is in positive direction of z, positive magnitudes, otherwise it is negative. That you can see that for the yellowish, greenish, and bluish, that you can see, and you can see a kind of recirculation. You can see here recirculation of the flow, that, okay, that the flow, exactly, you see that how the flow is just uh, back to the like this residuals of fluid that we have here. It is like a back flow here. Otherwise, after joining, you can see that you have the flow is joining very chaotic here, and this is maybe a little bit disturbances that you can see that here. Again, recirculation here. This is belongs to the to the surface waves that traveling on the sides of the free surface level and coming back from outlet toward the inlet. So this is good visualization that we can have. We can also use path line. I already defined that. It takes a little bit time to draw for us the path line from inlet toward outlet and over the free surface. It is also another good visualization aid here that we can have it for post processing of the results from Fluent. Okay, uh, as you can see here, okay, that the flow is developed and higher velocity when the merging started. Okay, and this is, maybe it is easier to see from the bottom view. Okay, you can see the way that it is like a recirculation of the streams, that we have very good view of these two streams, and then have they interact and then developed along along the main tube. On top of that, we can also work for the animations. Okay, it depends what we want to see. It depends. Okay, that okay, what we want to see here. I already prepared some of them. Let me show you. Okay, okay, this is one of them that you see that they have the flow uh, going up and down at the free surface. You see that have the flow level is fluctuating inside the main tunnel after merging water over the from the two branches. This is the free surface velocity over the distribution over the free surface. Have you see that have disturbed the free surface along with the water velocity, and have the wave, how wavy is the free surface is. Another one, again, for the volume of flow distribution, that shows that the water level inside the the, the domain. So hopefully I can, in this video, I could show you that how to set up volume of fluid method to simulate the free surface of the water inside some circular open channel that could be used for the modeling of the tubes or tunnels or underground tunnels. That we can see it here. We see different behavior of the flow compared to the pipe flow, that it is a kind of internal flow which is quite different compared to the open channel flow inside these tubes or tunnels. Thank you very much.